how big the universe really is. Welcome back to Nebula Nights. Tonight, we're going to explore a question that has captivated human minds for millennia, a question so vast that even attempting to answer it requires us to stretch our imagination beyond its comfortable limits. How big is the universe, really? Not just the numbers, though we'll discuss those, but the actual staggering, mind-bending scale of everything that exists. Settle in, get comfortable, because what we're about to explore together will fundamentally shift your perspective on existence itself. We're going to travel through space and time, measuring distances that dwarf anything in our daily experience, contemplating structures so immense they make our entire planet seem like less than a speck of dust, and peering into corners of reality so distant that the light reaching us began its journey when the universe itself was still in its infancy. The universe is bigger than you think. Much, much bigger. And the strange thing is, even that statement doesn't capture the full truth, because not only is the universe incomprehensibly vast, but most of it lies forever beyond our ability to see or measure. The universe we can observe, study, and understand represents just a tiny bubble in what may be an infinite ocean of existence. This realization sits at the heart of our cosmic journey tonight. When we ask how big the universe is, we're really asking two different questions. First, how big is the observable universe, the portion of reality from which light has had enough time to reach us? And second, how big is the entire universe, including all the regions that remain invisible to us, perhaps forever? These are profoundly different questions with profoundly different answers. Let me start by acknowledging something important. The human brain didn't evolve to comprehend cosmic scales. Our ancestors needed to judge distances between trees, estimate the size of approaching predators, and understand the layout of their immediate environment. Millions of years of evolution optimized our brains for understanding scales ranging from millimeters to kilometers. When we encounter distances measured in billions of light years, our intuition completely fails us. We can do the mathematics, we can make the measurements, but true comprehension slips through our mental fingers like water. So tonight, as we explore these vast distances, I won't pretend you'll walk away with an intuitive grasp of the universe's scale. That's impossible. What I can do is provide you with frameworks, comparisons, and context that will let you appreciate, if not fully comprehend, just how astonishingly large reality truly is. We'll build our understanding gradually, starting with distances we can relate to and slowly, patiently, expanding outward toward the edges of the observable universe and beyond. The journey begins with a simple acknowledgement of our starting point. We're sitting on Earth, a rocky planet with a diameter of about 12,742 kilometers. Our planet orbits a fairly average star, the Sun, at a distance of approximately 150 million kilometers. These distances, while large compared to our daily experience, remain within the realm of human comprehension. We can imagine traveling these distances. Our spacecraft have made these journeys, but even here, at the threshold of our cosmic exploration, we encounter something profound. The fastest human-made object, the Parker Solar Probe, travels at speeds reaching over 690,000 kilometers per hour relative to the Sun. At this incredible velocity, crossing the distance from Earth to the Sun would take roughly 9 days. Think about that. The absolute pinnacle of our technological achievement, moving faster than anything humanity has ever created, would need more than a week to bridge the gap between our world and our star, and that's just the beginning. That distance, 150 million kilometers, represents what astronomers call one astronomical unit. It's a convenient measuring stick for our solar system, a baseline from which we can describe the orbits of other planets. Neptune, the outermost planet in our solar system, orbits at about 30 astronomical units from the Sun. That means the distance from Earth to Neptune is roughly 30 times the distance from Earth to the Sun. Our speediest spacecraft would need years to make that journey. But even Neptune, distant as it seems, remains in our cosmic backyard. The solar system itself, if we include the outer boundary of the Oort cloud, a shell of icy objects surrounding our Sun, extends perhaps 100,000 astronomical units from the Sun. That's about 1.5 light years. A light year, remember, is the distance light travels in 1 year, moving at its constant speed of approximately 299,792 kilometers per second. In more everyday terms, that's about 9.5 trillion kilometers per year. Light moves fast, incomprehensibly fast. In the time it takes you to blink, about 1/3 of a second, light travels roughly 100,000 kilometers. That's enough to circle Earth's equator 2.5 times. In 1 second, light could travel from Earth to the Moon and back with time to spare. This speed, denoted by the letter c in physics equations, represents an absolute cosmic speed limit, a fundamental property of our universe that we'll return to later. Understanding distance, the cosmic distance ladder. Now, before we venture further into the depths of space, we need to understand something crucial. How do we actually know these distances? How can astronomers claim to measure the size of the universe when we can't even send a spacecraft to the nearest star? The answer lies in one of astronomy's most elegant achievements, the cosmic distance ladder. Imagine you're trying to measure the height of a distant mountain. You can't simply walk up to it with a measuring tape. Instead, you'd use geometry, measuring angles, and using nearby reference points to calculate the distance. Astronomers face this same challenge, but on an unimaginably grander scale. They've developed a series of overlapping measurement techniques, each building upon the previous one, allowing them to measure distances from nearby stars all the way to the edge of the observable universe. The first rung of this cosmic distance ladder is parallax, and it's the only truly direct method we have for measuring stellar distances. Parallax relies on a simple geometric principle. Hold your finger out at arm's length and look at it with one eye closed, then switch eyes. Your finger appears to shift position relative to the background. This apparent shift is parallax, and it occurs because your two eyes view your finger from slightly different positions. Astronomers use the same principle, but instead of using the distance between their eyes, they use Earth's orbit. They photograph a nearby star in January, then photograph it again in July, when Earth has moved to the opposite side of its orbit around the Sun. The baseline for this measurement is 2 astronomical units, twice the Earth-Sun distance. Even with this enormous baseline, the apparent shift of nearby stars is tiny, measured in fractions of a second of arc. 1 second of arc is 1/3600th of a degree. The nearest star to our Sun, Proxima Centauri, shows a parallax of about 0.76 seconds of arc. From this measurement, we can calculate that Proxima Centauri lies at a distance of about 4.2 light-years. That means the light we see from this star tonight left its surface over 4 years ago, when events happening on Earth were still in our recent past. When you look at Proxima Centauri, you're literally looking back in time. Parallax works beautifully for nearby stars, those within a few hundred light-years of Earth. The European Space Agency's Gaia spacecraft, which has been mapping stellar positions with unprecedented precision since 2014, has measured parallax distances to nearly 2 billion stars. These measurements form the foundation of the cosmic distance ladder, the bedrock upon which all greater distance measurements rest. But parallax has limits. Beyond a few tens of thousands of light-years, even with Gaia's exquisite precision, the parallax angle becomes too small to measure reliably. The stars simply don't shift enough against the distant background. So to measure greater distances, astronomers need a different approach. This is where the next rung of the cosmic distance ladder comes in: standard candles. A standard candle is any astronomical object whose true brightness we know. By measuring how bright it appears from Earth and comparing that to its known true brightness, we can calculate how far away it must be. It's like seeing a light bulb in the distance. If you know it's a 100-watt bulb, you can estimate its distance by how dim it appears. The most famous standard candles are Cepheid variable stars, named after Delta Cephei, the first star of this type to be studied in detail. These remarkable stars pulse, brightening and dimming with clockwork regularity. Some complete a cycle in just a few days, others take months. In 1912, astronomer Henrietta Swan Leavitt made a groundbreaking discovery while studying Cepheid variables in the small Magellanic Cloud, a nearby dwarf galaxy. She found that a Cepheid's pulsation period directly relates to its true brightness. Longer period Cepheids are intrinsically brighter than shorter period ones. This period luminosity relationship, now called Leavitt's law, revolutionized astronomy. It meant that by simply timing a Cepheid's pulsation period, astronomers could determine its true brightness. And knowing its true brightness while measuring its apparent brightness gave them the distance. Suddenly, astronomers had a reliable way to measure distances to other galaxies, as long as they could identify individual Cepheid variables within them. Edwin Hubble used this technique in the 1920s to make one of the most important discoveries in the history of astronomy. By measuring Cepheids in what was then called the Andromeda Nebula, he proved that this nebula was actually an entire galaxy, located far beyond the boundaries of our own Milky Way. The universe, previously thought to consist solely of our galaxy and nothing else, suddenly expanded to include countless other galaxies scattered through space. Cepheid variables can be used to measure distances up to about 100 million light-years. For even greater distances, astronomers turn to an even brighter standard candle, type Ia supernovae. These spectacular explosions occur when a white dwarf star in a binary system accumulates too much matter from its companion. When the white dwarf's mass reaches a critical threshold, called the Chandrasekhar limit, catastrophic runaway nuclear fusion ignites, obliterating the star in one of the most luminous events in the universe. What makes type Ia supernovae so valuable for distance measurement is their remarkable consistency. Because they always occur at the same mass threshold, they always release roughly the same amount of energy. This means they all reach approximately the same peak brightness. And because they're so brilliant, briefly outshining entire galaxies, they can be seen from billions of light years away. In the 1990s, two teams of astronomers used type Ia supernovae to measure distances to galaxies throughout the observable universe. They expected to find that the universe's expansion was slowing down, gradually decelerated by the gravitational pull of all the matter within it. Instead, they discovered something shocking. The universe's expansion is accelerating. This discovery, which earned the lead researchers the 2011 Nobel Prize in Physics, revealed that some mysterious force, which we now call dark energy, is pushing the universe apart. We'll return to this profound discovery later. At the farthest reaches of the observable universe, where even type Ia supernovae become too faint to see clearly, astronomers use another technique, redshift. This method exploits a consequence of the universe's expansion. As space itself stretches, the light traveling through that space gets stretched as well. This stretching increases the wavelength of light, shifting it toward the red end of the spectrum. The more distant a galaxy, the more the universe has expanded during the light's journey, and therefore, the more that galaxy's light is redshifted. By measuring a galaxy's redshift and comparing it to the distance measurements from type Ia supernovae in nearby galaxies, astronomers can establish a relationship between redshift and distance. This relationship, encoded in what's called the Hubble diagram, allows them to estimate distances to the most remote galaxies visible to our telescopes. Each rung of the cosmic distance ladder depends on the rung below it. Parallax measurements calibrate our understanding of Cepheid variables. Cepheids calibrate type Ia supernovae. Supernovae calibrate the redshift distance relationship. This interdependence means that errors accumulate as we climb the ladder. A small uncertainty in our parallax measurements propagates upward, affecting every subsequent distance estimate. This is why astronomers continually work to refine each rung, improving the precision of the entire ladder. The cosmic distance ladder represents more than just a clever set of measurement techniques. It embodies humanity's determination to understand the universe despite seemingly insurmountable obstacles. We can't visit distant galaxies or stretch measuring tapes across cosmic voids, but through careful observation, mathematical reasoning, and the fundamental laws of physics, we can nevertheless map the universe with stunning accuracy. The observable universe, our cosmic horizon. Now, armed with our understanding of how distances are measured, we can begin to grasp the true scale of the observable universe. And here we encounter our first truly mind-bending fact. The observable universe has a diameter of approximately 93 billion light-years. Wait, you might think, how can that be right? If the universe is only 13.8 billion years old and light travels at a finite speed, shouldn't we only be able to see objects that are 13.8 billion light-years away? Shouldn't the observable universe be, at most, 27.6 billion light-years across? This reasonable question highlights one of the most subtle and fascinating aspects of cosmology. The answer involves understanding that the universe itself is expanding, and that expansion affects the distances we measure in counterintuitive ways. Imagine a photon of light emitted from a galaxy in the early universe, let's say just 400 million years after the Big Bang. That photon begins traveling toward the location that will eventually become Earth, moving at the speed of light. Meanwhile, the universe continues expanding. The space between the photon's starting point and its destination is growing. The photon keeps moving forward, but new space keeps appearing in front of it, like trying to walk up a down escalator. Nevertheless, the photon persists. It travels for 13.4 billion years before finally reaching Earth and entering a telescope. During those 13.4 billion years, the galaxy that emitted the photon has been carried away by the expansion of space. That galaxy, which was perhaps only a few billion light years away when the photon started its journey, is now roughly 46 billion light years distant. This is the key insight. Light travel time and current distance are not the same thing. The observable universe extends to the current locations of objects whose light has had time to reach us, not to the distance those objects were from us when they emitted that light. Because space has been expanding throughout the universe's history, objects that emitted light in the distant past have since moved much farther away. The furthest distance from which light can reach us, given the age and expansion history of the universe, is about 46.5 billion light-years in any direction. This radius defines what astronomers call the particle horizon. Beyond this horizon, light simply hasn't had enough time to reach us, even if it began traveling at the instant of the Big Bang. Multiply this radius by 2, and you get the diameter of the observable universe, 93 billion light-years. Let's pause here to truly appreciate what this means. The observable universe is a sphere centered on Earth, extending 46.5 billion light-years in every direction. Everything we can see, everything we can detect with any telescope, everything that has ever entered our cosmic consciousness exists within this sphere. And make no mistake, this sphere is vast beyond human comprehension. To put this in perspective, consider that traveling at the speed of light, the fastest possible speed in our universe, it would take 93 billion years to cross the observable universe from edge to edge. Our entire solar system, from the sun to the outer reaches of the Oort cloud, spans about 2 light years. The entire solar system would fit into the observable universe roughly 46 billion times along one axis. The Milky Way galaxy, our cosmic home containing hundreds of billions of stars, spans about 100,000 light years. You could line up 930,000 Milky Ways from one edge of the observable universe to the other. These comparisons help illustrate the scale, but they still don't quite convey the overwhelming vastness. Perhaps it helps to think about volume. The observable universe contains approximately 400 trillion billion cubic light years. That's a 4 followed by 51 zeros. Every cubic light year of space, of which there are incomprehensibly many, could contain multiple stars and their planetary systems. At the edge of the observable universe, we find some of the most ancient light in existence, the cosmic microwave background radiation. This radiation, which fills all of space, consists of photons that have been traveling freely through the universe for 13.8 billion years, ever since the universe cooled enough for atoms to form and light could travel unimpeded. The cosmic microwave background represents our ultimate horizon, the furthest back in time we can see with light of any wavelength. Before the emission of the cosmic microwave background, the universe was opaque, filled with a hot plasma where photons couldn't travel freely. Looking at the cosmic microwave background is like seeing the moment when the cosmic fog cleared, revealing the universe for the first time. This radiation, discovered accidentally in 1965 by Arno Penzias and Robert Wilson, provides our most direct view of the infant universe, a snapshot taken when the cosmos was just 380,000 years old. But the observable universe is not static. It's continually growing. Right now, at this very moment, light from previously invisible regions is entering our observable sphere for the first time. Every second, the observable universe expands by 1 light second in every direction. Every year, it grows by 1 light year. Galaxies that were once beyond our particle horizon are crossing into visibility, their ancient light finally completing its cosmic journey. However, this expansion comes with a bittersweet realization. While new regions are entering our observable universe, others are slipping away. The accelerating expansion of the universe, driven by dark energy, means that very distant galaxies are receding from us faster than light can travel. These galaxies are moving beyond our cosmic event horizon, a boundary marking regions from which light emitted today will never reach us, no matter how long we wait. Once a galaxy crosses this boundary, it fades from view forever, consigned to permanent invisibility. This cosmic event horizon currently lies about 16 billion light-years away. Galaxies beyond this distance are receding so fast that any light they emit now will never overcome the expansion of space to reach Earth. They will continue to fade, their light increasingly redshifted, until they wink out entirely from our view. In the distant future, if the accelerating expansion continues, galaxies beyond our local group will disappear from the night sky, leaving future astronomers with a much emptier universe to observe. A universe of galaxies. Within the observable universe, spread across those 93 billion light-years, we find galaxies. Countless galaxies. Vast islands of stars, gas, dust, and dark matter, each one a complex ecosystem where stars are born, live, and die, where planetary systems form, where perhaps other civilizations look up at their own night skies and wonder about their place in the cosmos. Estimating the total number of galaxies in the observable universe has been a major goal of astronomy for decades. Early estimates, based on the Hubble Deep Field images captured in the mid-1990s, suggested around 100 to 200 billion galaxies. These images, created by pointing the Hubble Space Telescope at a tiny patch of seemingly empty sky for days on end, revealed thousands of faint, distant galaxies where none had been visible before. Extrapolating this density across the entire observable universe yielded the 100 billion estimate. But this number was wrong, dramatically wrong. In 2016, an international team led by Christopher Consolis used deeper images and more sophisticated analysis to reach a startling conclusion. The observable universe contains at least 10 times more galaxies than previously thought. Their best estimate, 2 trillion galaxies. 2 trillion is a number that strains comprehension. Written out, it's 2 million million, or 2,000 billion. If you started counting galaxies, 1 per second, 24 hours a day, it would take you over 63,000 years to count them all. And these aren't just points of light. Each of these 2 trillion galaxies contains millions, billions, or even hundreds of billions of stars. The Milky Way alone hosts an estimated 200 to 400 billion stars. Multiply that by 2 trillion galaxies, and you get a number of stars that's almost meaningless in its enormity. Some estimates suggest around 1 septillion stars in the observable universe. That's a 1 followed by 24 zeros. This number exceeds the total number of grains of sand on all of Earth's beaches and deserts combined. It exceeds the number of cells in every human body that has ever lived. It's a number so large that if you tried to count it, assigning 1 second to each star, you would need roughly 30 trillion years, more than twice the current age of the universe. But even this staggering figure comes with an important caveat. Most of these galaxies remain unseen. The 2 trillion estimate includes galaxies too faint and too distant to detect with current technology. Consolis' team calculated that about 90% of galaxies in the observable universe lie beyond the reach of even our best telescopes. They're too small, too faint, too far away. Their light has been weakened by distance and redshifted by expansion until it becomes nearly impossible to distinguish from the background noise of space. These invisible galaxies aren't just smaller versions of the galaxies we know. Many of them are ancient, primitive systems from the universe's youth. In the early universe, galaxies were more numerous, but smaller and less organized than today's massive spiral and elliptical galaxies. Over cosmic time, these small galaxies have merged together, their gravitational attraction pulling them into collision and fusion, creating fewer but larger galaxies. This hierarchical process of galaxy formation means that looking back to the early universe reveals a denser population of smaller galaxies, many of which have now merged to form the large galaxies we see nearby. The James Webb Space Telescope, launched in December 2021 and operational since mid-2022, has begun revealing some of these previously invisible galaxies. With infrared sensitivity far exceeding Hubble's capabilities, Webb can detect the highly redshifted light from extremely distant galaxies, pushing our observations deeper into cosmic history than ever before. In May 2024, Webb confirmed the discovery of JADES GS Z14-0, currently the most distant galaxy ever observed. This galaxy appears as it was just 290 million years after the Big Bang, when the universe was merely 2% of its current age. The light we see from this galaxy has been traveling for over 13.5 billion years, crossing nearly the entire observable universe to reach us. Looking at this galaxy, we're seeing stars that formed when the universe itself was still learning how to make galaxies. What makes JADES GS Z14-0 particularly remarkable is its unexpected brightness and size. Early theoretical models predicted that galaxies in this era should be small, dim, and still in the process of formation. Instead, Webb found a galaxy over 1,600 light-years in diameter, bright and actively forming stars. This discovery challenges our understanding of how quickly galaxies could form in the early universe. It suggests that the first galaxies assembled faster and more efficiently than we previously thought possible. The galaxy appears bright, not because of a massive black hole at its center, which would create a quasar-like beacon, but because of young stars forming in abundance. These stars, made primarily from the hydrogen and helium created in the Big Bang, represent some of the earliest stellar populations in cosmic history. Studying these stars helps astronomers understand how the first generations of stars seeded the universe with heavier elements, elements that would eventually become planets, and ultimately, life. JADES GS Z14-0 isn't alone in the early universe. Webb has discovered numerous galaxies from this epoch, each one revealing new surprises about cosmic dawn, the period when the first stars illuminated the previously dark universe. Another galaxy, GNZ11, observed at a time just 430 million years after the Big Bang, shows evidence of an actively feeding supermassive black hole at its center. This discovery raises fascinating questions about how black holes could grow so massive so quickly in the early universe. Galaxies come in an astonishing variety of forms and sizes. Some, like our Milky Way, are graceful spirals with elegant arms wrapped around a central bulge. Others are smooth ellipticals, enormous clouds of old stars with little structure. Still others are irregular, chaotic collections of gas and stars with no organized form. The largest galaxies stretch more than 1 million light-years across, 50 times bigger than our Milky Way. The smallest are dwarf galaxies, containing just millions of stars, barely visible smudges on the cosmic landscape. Between these extremes, we find galaxies of every intermediate size and type. Barred spirals with elongated cores, lenticular galaxies that blend properties of spirals and ellipticals, ring galaxies with stellar loops encircling their centers, and peculiar galaxies whose strange shapes reveal recent interactions or collisions. Each galaxy tells a story of formation, evolution, and interaction with its environment. Our own Milky Way, while certainly impressive, is fairly typical by cosmic standards. It's a spiral galaxy about 100,000 light-years across, containing somewhere between 200 and 400 billion stars. The Sun, along with our entire solar system, orbits the galactic center at a distance of about 26,000 light-years, completing one orbit every 230 million years. Every star visible in the night sky from Earth belongs to the Milky Way. Every constellation, every bright point of light, every astronomical object visible without a telescope exists within our galaxy. The Milky Way is part of a larger structure called the Local Group, a collection of more than 50 galaxies bound together by gravity. The Local Group spans about 10 million light-years and includes 3 large galaxies, the Milky Way, Andromeda, and Triangulum, along with dozens of smaller dwarf galaxies. Andromeda, also known as Messier 31, is the closest large galaxy to our own, located about 2.5 million light-years away. When you look at Andromeda in the night sky, you're seeing light that left the galaxy when our distant ancestors were learning to use stone tools, long before modern humans emerged as a species. Andromeda and the Milky Way are approaching each other at about 110 kilometers per second. In roughly 4.5 billion years, they will collide. But this collision won't be catastrophic in the way we might imagine. Galaxies are mostly empty space, with vast distances between individual stars. When galaxies collide, the stars themselves rarely impact each other. Instead, the galaxies pass through each other like two clouds merging, their gravitational interaction distorting their shapes and triggering new waves of star formation. Eventually, Andromeda and the Milky Way will merge into a single, larger, elliptical galaxy that astronomers have already nicknamed Milkomeda. The speed of light, time's messenger. Before we venture further into the cosmos, we need to return to something we touched upon earlier, the speed of light. This speed, this fundamental constant of nature, shapes everything about how we perceive and measure the universe. Light doesn't just illuminate the cosmos, it defines our relationship with it. Light moves at exactly 299,792,458 meters per second in vacuum. This speed, usually denoted by the lowercase letter c, is one of the most precisely measured quantities in all of physics. It's so fundamental that scientists have actually defined the meter based on this speed. 1 meter is now officially defined as the distance light travels in 1/299,792,458th of a second. This speed seems fast by human standards, and it is. In 1 second, light travels far enough to circle Earth's equator 7.5 times. A beam of light could travel from New York to Tokyo and back in the time it takes you to snap your fingers. Yet, despite this incredible velocity, light still takes time to cross cosmic distances, and this travel time has profound implications for how we observe and understand the universe. From the moon, light reaches Earth in about 1.3 seconds. This means when we look at the moon, we see it not as it is now, but as it was just over a second ago. From the sun, light takes approximately 8 minutes and 20 seconds to reach us. If the sun suddenly vanished, we wouldn't know about it for more than 8 minutes. We'd continue to see the sun, feel its warmth, and experience its light for those 8 minutes, living in a present that had already become the past. The implications become more striking as we look at more distant objects. Light from Jupiter takes about 43 minutes to reach Earth when the planet is at its closest. Mars, depending on its position in its orbit, can be anywhere from 4 to 24 light minutes away. This means that when Mars rovers like Perseverance execute commands, ground controllers must send signals that take several minutes to arrive, then wait several more minutes for confirmation. There's no way around this delay. It's imposed by the fundamental structure of space-time itself. Beyond our solar system, these light travel times stretch to years, then centuries, then millennia. Proxima Centauri, the nearest star beyond our sun, is 4.2 light-years distant. When we observe this star, we see it as it was when the last US presidential election was taking place. Sirius, the brightest star in our night sky, lies 8.6 light-years away. Its light left its surface around the time smartphones became ubiquitous in developed countries. The North Star, Polaris, stands 433 light-years distant. The light we see from Polaris tonight began its journey when Renaissance artists were painting masterpieces in Europe, when Shakespeare was still writing his plays. The Orion Nebula, that stunning stellar nursery, visible to the naked eye in winter skies, lies about 1,300 light-years away. The light from this region began traveling toward Earth around the time medieval Europe was experiencing the high Middle Ages, when Genghis Khan was beginning his conquests. When we photograph the Orion Nebula, we're not capturing an image of what's happening there now. We're preserving a moment from Earth's historical past, a moment when the light we're detecting departed from clouds of gas and newly forming stars. This time delay transforms every telescope into a time machine. When we observe distant galaxies, we don't see them as they are today. We see them as they were when their light began its journey toward us. The further away something is, the further back in time we see. This isn't a limitation of our instruments or a trick of observation. It's a fundamental feature of living in a universe where information travels at a finite speed. Looking at a galaxy 1 billion light years away, we see that galaxy as it existed 1 billion years ago, when the universe was noticeably younger, and that galaxy was still in an earlier stage of its evolution. Looking at JD's GS Z14-0, we see a galaxy as it appeared just 290 million years after the Big Bang, witnessing an epoch when the universe was still in its infancy, when the first galaxies were still coalescing from the primordial gas that filled space. This light speed delay has another consequence that's easy to state, but difficult to fully appreciate. We can never see what distant objects look like right now. There is no cosmic now. When we look at Andromeda, we see it as it was 2.5 million years ago. Whatever is happening in that galaxy at this very moment, whatever stars are exploding, whatever new planetary systems are forming, we won't know about it for 2.5 million years. The Andromeda we see tonight is the Andromeda of the early Pleistocene epoch on Earth, a time when our ancestors were primitive hominids just beginning to use the simplest stone tools. The speed of light also represents a cosmic speed limit, a maximum velocity that nothing with mass can reach. Albert Einstein's special theory of relativity, published in 1905, showed that this speed limit isn't arbitrary. It's woven into the fundamental structure of space and time. Moving objects experience time dilation, where time passes more slowly for them relative to stationary observers. As an object approaches the speed of light, this time dilation becomes more extreme. At exactly the speed of light, time would stop entirely. But reaching this speed requires infinite energy for any object with mass, making it impossible. Only massless particles can travel at the speed of light. Photons, the particles of light, always move at exactly this speed in vacuum. They can never be at rest. From a photon's perspective, if photons could have perspectives, the journey from a distant galaxy to your eye happens instantaneously, even if that journey takes billions of years from our frame of reference. This is one of the profound oddities of relativity. The subjective experience of time depends on motion and gravity. The finite speed of light also means that distant events may have already happened, but we won't know about them until their light reaches us. Stars may have already exploded, galaxies may have already collided, black holes may have already merged, but until the light from these events completes its journey to Earth, they remain unknown to us. The universe we see is a patchwork of different times, each region frozen at the moment its light left for our telescopes. This creates a peculiar situation. When we look at very distant galaxies, we see them as they were billions of years ago. Those galaxies have continued to evolve since then. They've formed new stars, perhaps hosted civilizations, possibly even been destroyed in collisions. But we can't see any of that. The light carrying information about those events is still traveling through space and won't reach us for billions of years. In a very real sense, the universe we observe is the universe of the past, a cosmic archaeological record written in light. The earliest reaches, cosmic dawn. With our understanding of light, distance, and time now firmly established, we can appreciate what it means to peer toward the edge of the observable universe. Here, in these furthest reaches, we're not just looking at distant places. We're looking at distant times, watching the universe as it was when it was young, violent, and still finding its form. The epoch from a few 100 million years to about 1 billion years after the Big Bang is called cosmic dawn, and it represents one of the most crucial periods in cosmic history. This was when the universe transitioned from a dark, nearly featureless expanse to a cosmos lit by the first stars and galaxies. Understanding this transition, mapping when and how it occurred, has been a central goal of cosmology for decades. Before cosmic dawn, the universe had been dark for millions of years. After the cosmic microwave background was emitted, about 380,000 years after the Big Bang, the universe entered what astronomers call the Dark Ages. During this period, the universe was filled with neutral hydrogen gas, but no stars had yet formed to illuminate this gas. The universe was literally dark, devoid of visible light beyond the slowly cooling cosmic microwave background radiation. Over time, gravity began pulling this gas into denser and denser clumps. in the densest regions, where matter accumulated fastest, the first stars began to form. These weren't stars like our sun. They were massive, perhaps hundreds of times more massive than the sun, burning hot and bright, but living short, violent lives. When these first stars died in supernova explosions, they scattered heavier elements, forged in their cores and in the explosion itself, into the surrounding space. These elements, including carbon, oxygen, nitrogen, and iron, would become crucial for later generations of stars and planets. The first galaxies formed from collections of these early stars. Initially small and irregular, these proto-galaxies were much less organized than the elegant spirals and ellipticals we see in the nearby universe. They were chaotic, violent places, where stars formed at prodigious rates and supermassive black holes began growing at galaxy centers. These early galaxies pumped out intense ultraviolet radiation that gradually ionized the hydrogen gas filling space, stripping electrons from atoms and making the universe transparent to light once again. The James Webb Space Telescope was specifically designed to study this epoch. Its large mirror and infrared sensitivity allow it to detect the highly red-shifted light from these first galaxies, seeing them as they were during and shortly after cosmic dawn. And what Webb has found has been nothing short of revolutionary. JADES GS Z14-0, discovered in observations made in October 2023 and January 2024, represents the current record for the most distant confirmed galaxy. At a redshift of about 14.3, this galaxy appears as it was just 290 million years after the Big Bang. Think about this timing. The universe was only 2% of its current age. On a cosmic calendar where the entire history of the universe is compressed into a single year, we're looking at a galaxy that existed on January 2nd, roughly one day after the universe began. What makes this galaxy so surprising isn't just its distance, but its properties. Early models of galaxy formation predicted that galaxies at this epoch should be small, dim, and still in the process of assembling. Instead, JADES GS Z14-0 is large, spanning over 1,600 light-years, and remarkably bright. It's producing stars at a tremendous rate, with massive amounts of gas being converted into new stars every year. The galaxy's brightness comes from young, hot stars rather than an active, supermassive black hole, which can also produce intense luminosity. This stellar origin for the light implies that large numbers of stars had already formed by this early epoch. The spectrum of the galaxy shows the presence of elements heavier than hydrogen and helium, indicating that earlier generations of stars must have already lived and died, enriching the gas from which JADES GS Z14-0's stars formed. This rapid formation timeline challenges our models of early galaxy assembly. Theoretical simulations suggested that building such a large, luminous galaxy should take longer. The universe at 290 million years old was still very young, and there hadn't been much time for gravity to pull matter together into large structures. Yet here, we have evidence that nature found a way to form substantial galaxies very quickly after the Big Bang. JADES GS Z14-0 isn't alone. Webb has discovered another extremely distant galaxy, JADES GS Z14-1, which is nearly as far away, seen at about 310 million years after the Big Bang. Together, these galaxies are teaching astronomers about the pace of early galaxy formation. They're showing us that the first galaxies assembled faster and more efficiently than we expected. Another remarkable galaxy, GN-Z11, lies at a redshift of about 10.6, placing it roughly 430 million years after the Big Bang. Webb's observations revealed that this galaxy hosts an actively feeding supermassive black hole at its center. The black hole, with a mass of at least 2 million times that of our Sun, is accreting matter at a tremendous rate, producing powerful winds that are blowing gas out of the galaxy at speeds of thousands of kilometers per second. The existence of such a massive black hole so early in cosmic history poses another puzzle. Black holes grow by accumulating matter, but there simply hasn't been much time since the Big Bang for a black hole to grow this large by standard processes. This suggests that either supermassive black holes formed through some rapid process in the early universe, or they had seed black holes that were already quite massive to begin with, perhaps formed directly from collapsing clouds of gas rather than from stellar remnants. Webb has also detected population 3 star candidates, the hypothetical first generation of stars that formed from primordial gas containing only hydrogen and helium with no heavier elements. These stars are predicted to be very massive, extremely hot, and very luminous. Their signature would be the presence of ionized helium without the presence of heavier elements. In the halo surrounding GNZ11, Webb's instruments detected a clump of gas that appears to be pristine, containing helium but lacking heavier elements. This could be a region where population 3 stars are forming, offering a glimpse of stellar formation in its most primitive form. Every new discovery from Webb's observations of cosmic dawn rewrites our understanding of this crucial epoch. Each galaxy discovered, each supermassive black hole found, each chemical signature detected adds another piece to the puzzle of how the universe evolved from the smooth, nearly featureless state seen in the cosmic microwave background to the rich, structured cosmos we inhabit today. These observations also remind us of the dynamic nature of discovery. The current distance record held by JD's GS Z14-0 will almost certainly be broken. Webb is just beginning its exploration of the early universe. As astronomers analyze more data and push the telescope to its limits, they expect to find even more distant galaxies, pushing our observations ever closer to the Big Bang itself. Theoretical calculations suggest Webb might be able to detect galaxies as they appeared just 100 million years after the Big Bang, though finding such galaxies will require deep observations and considerable luck. But there's a limit. Even Webb cannot see past the cosmic microwave background. Before the universe was 380,000 years old, it was filled with opaque plasma. Light couldn't travel freely through this hot, dense fog of particles. The cosmic microwave background represents our ultimate horizon for electromagnetic observations. Everything that happened before the emission of this radiation remains invisible to light-based telescopes, hidden behind a curtain we cannot penetrate with conventional astronomy. The cosmic web, architecture of everything galaxies, are not scattered randomly through space. Step back far enough, survey a large enough volume, and structure emerges. Galaxies cluster into groups. Groups cluster into larger structures called clusters, and these clusters themselves arrange into an even grander pattern, a vast cosmic web that pervades the entire observable universe. This cosmic web represents the largest known structure in the universe. It consists of enormous filaments, vast sheets, and immense voids, creating a pattern that resembles soap foam or a spider's web stretched across billions of light years. The filaments, where most galaxies reside, can extend for hundreds of millions of light years, while the voids between them contain very few galaxies and can span similar distances. The cosmic web formed through the action of gravity on the slight density variations present in the early universe. Just after the Big Bang, the universe was remarkably uniform, but not perfectly so. Quantum fluctuations during the inflationary epoch created tiny variations in density, regions that were slightly denser or slightly less dense than average. These variations, preserved in the cosmic microwave background as tiny temperature fluctuations, were the seeds of all the structure we see today. Over time, gravity amplified these initial variations. Regions that were slightly denser than average attracted more matter, becoming progressively denser. Regions that were slightly less dense saw matter leave them, becoming even emptier. This process created a network of dense filaments separated by underdense voids. Dark matter, which doesn't interact with light but does interact through gravity, played a crucial role in this process, providing most of the gravitational pull that shaped the cosmic web. Galaxy filaments are the threads of this cosmic web. These are elongated structures, typically tens to hundreds of millions of light years long, where galaxies congregate. The filaments mark regions of higher than average density, where matter has collected into sheets and strands. Along these filaments, galaxies often arrange themselves in chains or walls, creating visually striking patterns when we map the large-scale structure of the universe. Some of the longest known filaments stretch truly staggering distances. the Hercules Corona Borealis Great Wall, discovered in 2013 using gamma-ray burst data, extends more than 10 billion light-years across. This structure is so large that light takes over 10 billion years to cross it. If you could somehow travel at the speed of light along this structure, by the time you reach the other end, the universe would be almost as old again as it was when you started. Another enormous structure, called the Sloan Great Wall, spans about 1.37 billion light-years. Discovered in 2003 using data from the Sloan Digital Sky Survey, this structure consists of a vast wall of galaxies interconnected by filaments of dark matter and intergalactic gas. The Sloan Great Wall includes numerous galaxy clusters, each containing hundreds to thousands of galaxies, all linked in a grand cosmic architecture. Where filaments intersect, we find galaxy clusters, the densest concentrations of galaxies in the universe. These clusters can contain anywhere from hundreds to thousands of galaxies, bound together by their mutual gravitational attraction. The Coma cluster, for instance, contains over 1,000 identified galaxies and lies about 320 million light-years away. The Virgo cluster, which our own local group of galaxies is slowly falling toward, contains about 2,000 galaxies and spans about 15 million light-years. Galaxy clusters are more than just collections of galaxies. They're also filled with hot gas, millions of degrees in temperature, that emits X-rays and outweighs all the visible matter in the cluster's galaxies combined. This gas, heated by the cluster's formation and by energy from supermassive black holes at galaxy centers, helps astronomers study cluster properties and trace the distribution of dark matter. Dark matter, though invisible to telescopes, reveals its presence through gravitational effects. In galaxy clusters, the distribution of dark matter can be mapped by observing how the cluster's gravity bends light from background galaxies, a phenomenon called gravitational lensing. These observations show that dark matter forms an invisible scaffold, a framework on which visible matter arranges itself. The cosmic web we observe in galaxy distributions is really tracing the underlying web of dark matter that dominates the universe's mass. Between the filaments lie the cosmic voids. These are enormous regions, typically 30 to 300 million light-years across, that contain very few galaxies. Voids aren't completely empty, but they're dramatically underdense compared to filaments and clusters. If you were somehow transported to the center of a large void, looking around in every direction, you might see only a handful of distant galaxies against the darkness of space. The nearest neighboring galaxies could be tens of millions of light-years away. The largest known void, the Boötes void, spans approximately 330 million light-years and contains only about 60 galaxies, where we would expect to find thousands based on average cosmic density. Discovered in 1981 by Robert Kirshner and colleagues, the Boötes void represents about 0.27% of the observable universe's diameter. Yet within this seemingly empty region, any hypothetical observers would see a very different view of the universe than we do, with far fewer galaxies visible in their night sky. Voids, despite their emptiness, play an important role in understanding cosmology. The shapes and sizes of voids depend sensitively on the universe's expansion history and the properties of dark energy. By studying how voids evolve over cosmic time, comparing voids at different distances and therefore different look-back times, astronomers can test theories of cosmic acceleration and constrain the properties of dark energy. The cosmic web is not static. It's constantly evolving as gravity continues to pull matter together. Galaxy clusters grow as smaller groups fall into them along filaments. Voids expand as matter drains out of them into denser regions. This ongoing evolution means that the cosmic web looked different in the past and will look different in the future. Observations of distant galaxies, seeing the universe at earlier epochs, show us a cosmic web that was less developed, with less pronounced filaments and shallower voids. All of this structure, from individual galaxies to the cosmic web itself, emerged from incredibly subtle variations in density in the early universe. The temperature fluctuations in the cosmic microwave background, the fingerprints of these initial variations, show density contrasts of only about 1 part in 100,000. Gravity amplified these tiny differences over billions of years, transforming them into the vast structures we see today. This process represents one of the most elegant examples of how simple laws of physics, operating over cosmic timescales, can produce enormous complexity. Expansion and dark energy, the accelerating cosmos. The universe is not static. This might seem obvious now, but for most of human history, it was assumed that the cosmos was eternal and unchanging. Even Einstein initially believed in a static universe, introducing his cosmological constant to prevent gravitational collapse in his general relativity equations. The discovery that the universe is expanding ranks among the most important findings in the history of science, fundamentally altering our understanding of cosmic history and destiny. Edwin Hubble made this discovery in the late 1920s using observations of Cepheid variables in distant galaxies. By measuring their distances and comparing them to their velocities, determined from redshifts, Hubble found a clear relationship. More distant galaxies were moving away faster. This observation could only be explained if space itself was expanding, carrying galaxies apart like raisins in rising bread dough. This expansion has a profound implication. If galaxies are moving apart now, they must have been closer together in the past. Running the expansion backward, we arrive at a moment when everything was in the same place, compressed into an infinitesimally small point of infinite density. This is the Big Bang, not an explosion in space, but the explosive expansion of space itself. The universe didn't expand into pre-existing space. Space, time, and all the matter and energy in the universe came into existence together at this moment. For decades after Hubble's discovery, astronomers debated the universe's ultimate fate. Would the expansion continue forever, with galaxies drifting further apart eternally? Or would gravity eventually halt the expansion, perhaps even reversing it to create a big crunch where all matter collapses back together? The answer, scientists believed, depended on how much matter the universe contained. Too little, and gravity couldn't stop the expansion. Too much, and eventual collapse was inevitable. In the late 1990s, two teams of astronomers set out to measure the universe's expansion rate using type Ia supernovae as standard candles. These exceptionally bright explosions could be seen billions of light years away, allowing measurements of the expansion rate at different epochs in cosmic history. Both teams expected to find that the expansion was slowing down, decelerated by the gravitational pull of all the universe's matter. Instead, they discovered something shocking. The expansion wasn't slowing down at all. It was speeding up. Distant supernovae appeared fainter than expected, indicating they were further away than standard models predicted. The only explanation was that the universe's expansion had been accelerating for the past several billion years. This discovery, announced in 1998, stunned the scientific community. Something was counteracting gravity on cosmic scales, pushing galaxies apart with increasing force. Scientists dubbed this mysterious influence dark energy, not because it was understood, but simply to give it a name. Dark energy remains one of the deepest mysteries in physics. Cosmologists estimate that dark energy makes up about 68% of the universe's total energy content. Dark matter contributes about 27%, while ordinary matter, everything made of atoms, all the stars, planets, and gas we can see or detect, comprises just 5%. The universe is dominated by substances we don't understand, with the familiar matter of our daily experience relegated to a minor constituent. What is dark energy? Nobody knows for certain. The leading hypothesis is that it's a property of space itself, a fundamental energy that permeates every cubic centimeter of the universe. As the universe expands and more space comes into existence, more of this energy appears, causing the expansion to accelerate. Einstein's cosmological constant, which he introduced and then discarded, may have been right after all, representing this uniform energy density of space. The discovery of cosmic acceleration earned its lead researchers, Saul Perlmutter, Brian Schmidt, and Adam Rees, the 2011 Nobel Prize in Physics. Their work revealed that the universe's expansion history is more complex than anyone imagined. For the first several billion years after the Big Bang, the expansion did slow down, held back by gravity. But around 5 billion years ago, when the universe had expanded enough that matter density decreased sufficiently, dark energy took over, and acceleration began. This acceleration has profound implications for the universe's future. If dark energy remains constant, the universe will continue accelerating forever. Galaxies beyond our local group will recede faster and faster, eventually crossing beyond our cosmic event horizon and disappearing from view. In the distant future, hundreds of billions of years from now, an observer in our galaxy would see a very different universe, mostly empty space, with only the merged remnants of local galaxies visible, while the rest of the cosmos has receded beyond detection. The expansion rate of the universe is quantified by the Hubble constant, named after Edwin Hubble. This constant describes how fast galaxies are receding per unit of distance. Current measurements place the Hubble constant at approximately 70 kilometers per second per megaparsec. This means that for every megaparsec, about 3.26 million light-years of distance between us and a galaxy, that galaxy is receding an additional 70 kilometers per second faster. Interestingly, there's currently a discrepancy in measurements of the Hubble constant, called the Hubble tension. Direct measurements using Cepheids and supernovae give one value, while measurements derived from the cosmic microwave background give a slightly different, lower value. This discrepancy might indicate we're missing something important in our understanding of the universe's expansion history, or it might simply reflect systematic errors in one or both measurement methods. Resolving this tension is a major focus of current cosmological research. Dark energy's behavior over cosmic time is also uncertain. Has it always had the same strength, or has it evolved? Is it truly constant, or does its density change as the universe expands? These questions matter because different answers imply different fates for the universe. If dark energy strengthens over time, we could face a big rip, where acceleration becomes so extreme that it eventually tears apart galaxies, then stars, then planets, and finally atoms themselves. If dark energy weakens, we might return to a decelerating universe that eventually collapses in a big crunch. Recent measurements from the Dark Energy Spectroscopic Instrument, which began operations in 2021, have provided the most detailed map yet of the universe's expansion history. By measuring the positions and redshifts of millions of galaxies, the instrument has traced how dark energy has influenced the universe's expansion over the past 11 billion years. Early results suggest that dark energy's strength might not be perfectly constant, but could vary over time, though more data is needed to confirm this intriguing possibility. The universe's accelerating expansion also affects what we can observe. Light from galaxies beyond a certain distance will never reach us because those galaxies are receding faster than light can travel through the expanding space between us and them. This creates a fundamental limit to what we can ever see, even with perfect telescopes and unlimited time. The observable universe will not continue growing indefinitely. Eventually, as acceleration continues, the observable universe will begin to shrink as more galaxies cross beyond our cosmic event horizon and fade from view. Understanding dark energy represents perhaps the greatest challenge in modern physics. It requires us to grapple with the nature of space itself, to ask what it means for emptiness to possess energy, to confront the possibility that 95% of the universe consists of substances completely unlike anything in our everyday experience. Every telescope we build, every survey we conduct, every cosmological observation we make contributes pieces to this puzzle, gradually constraining the properties of this mysterious cosmic force that determines the universe's ultimate fate. Beyond the observable, the true universe. Everything we've discussed so far, every galaxy, every structure, every measurement, pertains to the observable universe, that finite sphere from which light has had time to reach us since the Big Bang. But here's the truly mind-bending question. How big is the entire universe? How large is the totality of existence, including all the regions beyond our cosmic horizon? The honest answer is we don't know. We can't know directly because we can't observe regions beyond our particle horizon. By definition, no information from those regions has reached us. They remain permanently invisible, forever inaccessible to our telescopes and instruments. Yet, we can make some educated guesses based on cosmological theories and the properties of the universe we can observe. First, there's no reason to think the universe suddenly ends at the edge of the observable region. The laws of physics appear to be the same everywhere we can measure them. The cosmic microwave background looks the same in all directions, suggesting the universe is homogeneous and isotropic on the largest scales, meaning it looks roughly the same everywhere and in all directions. If the observable universe is filled with galaxies, structures, and the cosmic web, it's reasonable to assume the rest of the universe is too. But how much bigger might the entire universe be? Some estimates, based on theories of cosmic inflation, suggest the entire universe is at least 250 times larger than the observable universe in every direction. This would mean the full universe contains at least 15 million times more volume than the observable universe. Those 2 trillion galaxies we can potentially see would represent just a tiny fraction of all galaxies in existence. The true number could be quadrillions, quintillions, or even more. Other calculations suggest the universe might be vastly larger still, perhaps thousands or even millions of times bigger than even these estimates. Some models allow for an infinite universe, extending forever in all directions with no edge or boundary. In an infinite universe, every possible configuration of matter that doesn't violate the laws of physics would occur somewhere, repeated infinitely many times across infinite space. The concept of an infinite universe challenges our intuition. How can something be infinite? What would that even mean? Yet, mathematically, infinity is a perfectly valid concept, and current observations don't rule it out. The curvature of space, which we can measure by studying the cosmic microwave background and the distribution of galaxies, appears to be very close to zero. A universe with zero curvature, called a flat universe, extends infinitely in all directions, just like an infinite flat plane. If the universe is infinite, then the observable universe is an infinitesimally small portion of the whole. Everything we can see, all the galaxies we've mapped, all the structures we've discovered, all the photons that have reached our telescopes since the beginning of time, represent essentially 0% of what exists. This is a humbling realization, to say the least. Even if the universe isn't infinite, if it's just vastly larger than the observable portion, the implications remain profound. The vast majority of reality lies beyond our ability to observe. Most galaxies will forever remain unknown to us. Most stars will never be cataloged. Most planets will never be discovered. The universe's history, its true scope, its ultimate nature, all remain partially or completely hidden from view. Some cosmologists have proposed that our universe might be just one region in a larger multiverse, a vast collection of separate, causally disconnected regions of spacetime, each potentially with different physical properties. In this scenario, our universe, even in its entirety, would represent just one bubble in an infinite foam of universes. These other universes would be forever unobservable, because no information can travel between them. They exist, if they exist at all, in a completely separate domain of reality. The multiverse hypothesis is controversial. Many scientists argue it's not truly scientific because it makes no testable predictions. If other universes are completely unobservable, what difference does their existence make? Others counter that the multiverse emerges naturally from certain versions of inflation theory and quantum mechanics, and that dismissing it simply because it's hard to test would be premature. Regardless of which scenario is correct, whether the universe is merely vast or truly infinite, whether it's alone or one among countless others, one thing is clear. The universe is far, far larger than the portion we can observe. Most of reality lies beyond our horizons, in regions we can never see, filled with galaxies we can never study, containing histories we can never know. This realization could be depressing. We're confined to observing just a tiny bubble of existence, with the vast majority of reality forever hidden from us. But I prefer to see it differently. The universe we can observe is already astonishingly vast, filled with wonders beyond number. 2 trillion galaxies, 1 septillion stars, structures spanning billions of light years, a cosmic web of magnificent complexity, all of this lies within our reach. Our telescopes can study galaxies from cosmic dawn. Our instruments can measure the subtle ripples in space-time from colliding black holes billions of light years away. Our minds can comprehend, at least mathematically, the scale and structure of the observable universe. That we can understand even this much is remarkable. That we, collections of atoms forged in stellar furnaces, arranged by evolution into thinking beings, can peer across billions of light years and reconstruct cosmic history, can measure the universe's age, composition, and fate, represents one of the greatest achievements of human civilization. The fact that more remains unknown, that vast regions lie beyond our horizons, doesn't diminish these accomplishments. If anything, it adds to the sense of wonder. Reality is larger, stranger, and more magnificent than we can observe. And that's exactly as it should be. Bringing it all together, perspective and wonder. So here we are, at the end of our journey through cosmic scales, having traveled from our tiny planet to the edge of the observable universe and contemplated what might lie beyond. Let's take a moment to collect our thoughts, to gather these vast distances and enormous numbers into something approaching perspective. The observable universe extends 46.5 billion light years in every direction, a sphere containing everything we can possibly see or detect. Within this sphere, 2 trillion galaxies wheel through space, each one a city of stars, many containing hundreds of billions of stellar systems. The total number of stars in the observable universe likely exceeds 1 septillion, a number so large it loses meaning, a quantity so vast it transcends comprehension. These galaxies are not scattered randomly, but arrange themselves in a magnificent cosmic web, filaments hundreds of millions of light years long, connecting galaxy clusters at their intersections, surrounding enormous voids that span similar distances. This web formed over billions of years through the action of gravity on tiny primordial density fluctuations, amplified from almost imperceptible variations into the grandest structures in existence. We see this universe not as it is, but as it was. Light, traveling at its tremendous but finite speed, takes time to cross cosmic distances. When we observe distant galaxies, we see them as they existed billions of years ago, watching their ancient light to reconstruct cosmic history. The furthest galaxies we've detected appear as they were when the universe was less than 300 million years old, still in its infancy, when the first stars were illuminating space for the first time. The universe itself is expanding, with space stretching and carrying galaxies apart. For billions of years, this expansion has been accelerating, driven by the mysterious dark energy that permeates all of space. This acceleration means that distant galaxies are receding from us faster and faster, many already moving faster than light relative to us, their light unable to overcome the expansion to reach us. In the distant future, if acceleration continues, galaxies beyond our local group will fade from view entirely, leaving a lonelier, emptier cosmos for any far future astronomers to observe. And all of this entire observable universe, with its trillions of galaxies and septillion stars, might represent just a tiny fraction of total reality. The entire universe could be hundreds of times larger, thousands of times larger, or even infinite, extending forever beyond our cosmic horizon. Most of existence could lie permanently beyond our ability to observe, forever hidden, forever unknowable. Now, let's bring this back to human scale for a moment. Let's remember where we started. We're sitting on Earth, a planet 12,742 kilometers in diameter. This planet is so small that you could walk around its circumference in about a year if you walked continuously. Yet this tiny world hosts millions of species, billions of humans, and uncountable individual stories and experiences. Every human drama, every triumph and tragedy, every civilization that has risen and fallen, every thought that has ever crossed a human mind, all of it happened here, on this small, rocky world. Our planet orbits an average star in an average galaxy, the Milky Way, which itself contains hundreds of billions of other stars. Our galaxy is just one of 2 trillion galaxies in the observable universe. Most of these galaxies lie so far away that their light takes billions of years to reach us. If a civilization existed in a distant galaxy and they pointed their telescopes toward the Milky Way, they wouldn't see us as we are now. They'd see our galaxy, as it was billions of years ago, long before the sun and Earth even formed, long before life emerged in our corner of space. This perspective can feel overwhelming. How can anything we do matter against such vast scales? How can human concerns carry any significance in a universe this large, this old, this strange? But I'd argue the opposite. The universe's vastness doesn't diminish the importance of our experiences. If anything, it amplifies them. We are, as far as we know, the universe's way of knowing itself. We are stardust, contemplating stars, matter pondering matter, consciousness emerging from the quantum interactions of particles forged in stellar cores. Every atom in your body was created either in the Big Bang or in the core of a dying star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in nuclear furnaces deep inside stars that lived and died billions of years ago. Those stars exploded, scattering their enriched material into space, where it eventually collected into new clouds, new stars, new planets. Our solar system formed from such a cloud, incorporating material from dozens or hundreds of previous stellar generations. You are literally made of star stuff, a collection of atoms billions of years old, arranged into a pattern that can think and wonder and ask questions about its place in the cosmos. The fact that we can understand the universe at all is extraordinary. Nothing in the laws of physics requires consciousness to emerge. Nothing demands that the universe produce beings capable of studying it. Yet here we are, building telescopes to peer across billions of light years, developing mathematical frameworks to describe cosmic evolution, unraveling the mysteries of dark matter and dark energy, mapping the cosmic web, and pushing ever deeper into space and time to witness cosmic dawn. Our scientific achievements represent a testament to human curiosity and determination. Every distance we've measured, every galaxy we've cataloged, every cosmic mystery we've even partially solved required decades or centuries of work by thousands of scientists, engineers, and theorists. The cosmic distance ladder wasn't built in a day. The discovery of cosmic acceleration required decades of work, perfecting standard candles and building surveys. The James Webb Space Telescope took 30 years from initial concept to first science images. These achievements are collaborative across generations. Astronomers today build on measurements made by their predecessors. Theories developed decades ago inform current observations. The Hubble Space Telescope, launched in 1990, has been making observations for over 30 years, providing data that enabled discoveries its designers never imagined. The foundations of cosmology were laid in the early 20th century, yet we're still building upon Einstein's relativity and Hubble's expansion law today, and the work continues. Even as I speak, these words, new telescopes, are being planned and built. The extremely large telescope in Chile, with a mirror 39 meters across, will gather 15 times more light than the largest telescopes operating today when it begins science operations around 2028. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will survey enormous areas of sky, mapping billions of galaxies to constrain dark energy's properties and trace cosmic structure evolution. Each new instrument, each new technology, each new theoretical insight pushes our understanding further. Questions that seemed unanswerable become tractable. Mysteries that seemed impenetrable yield to patient observation and careful analysis. The universe, despite its vastness and strangeness, reveals itself to those willing to look carefully and think deeply. Perhaps most remarkably, the universe appears to be comprehensible. The same laws of physics that operate in laboratory experiments on Earth govern the behavior of galaxies billions of light years away. The equations we write down to describe quantum mechanics, relativity, and thermodynamics apply everywhere in the observable universe and presumably beyond. The universe plays by rules, and those rules can be discovered, understood, and used to make predictions. This comprehensibility is not obvious or inevitable. The universe could have been chaotic, with different laws operating in different regions, or no consistent laws at all. Instead, we find elegant mathematical relationships, symmetries, and conservation laws that hold throughout space and time. This deep orderedness, this mathematical beauty underlying physical reality, has inspired scientists for centuries and continues to drive research today. As we conclude our cosmic journey, I want to emphasize something important. Understanding the universe's scale doesn't require memorizing numbers or mastering complex mathematics. What matters is developing a sense of perspective, an appreciation for the extraordinary nature of reality. The universe is bigger than we can comprehend, older than human civilization, and stranger than our everyday experience suggests. Yet it's also knowable, at least partially. We can measure it, map it, and understand how it works. This knowledge comes with responsibilities. We know now that Earth is a tiny outpost in an enormous cosmos. We know that we're alone in the observable universe as far as we can currently tell, though perhaps not permanently. We know that the conditions necessary for life as we know it are delicate, requiring the right kind of star, the right kind of planet, the right kind of atmosphere, the right location in the galaxy. Earth might be common, or it might be exceedingly rare. We don't yet know. What we do know is that this planet, this pale blue dot, suspended in a sunbeam, as Carl Sagan beautifully described it, is currently the only home we have. Every person you've ever known or heard of, every human life that's ever been lived, has been lived here, within a few kilometers of this planet's surface. The vast universe beyond, for all its wonders, remains inhospitable to human life, except for tiny pockets we can carve out through technology. We are adapted to Earth, to its gravity, its atmosphere, its temperature, its ecosystem. Preserving this precious world matters not just for its own sake, but because it's our only viable home for the foreseeable future. Looking up at the night sky, seeing stars that are actually suns like ours, some with their own planets orbiting them, knowing that many of those stars exist in distant galaxies billions of light years away, creates a profound sense of connection to the cosmos. We are not separate from the universe. We are part of it, intimately and fundamentally. The atoms in your body cycled through multiple stellar generations before assembling into you. The energy that powers your thoughts comes from food, which got its energy from the sun, which generates energy through nuclear fusion, the same process that powers every star in the universe. This cosmic perspective can be both humbling and empowering. Humbling because it reminds us how small we are, how brief our lives are against cosmic timescales, how limited our influence is compared to the forces that shape galaxies and drive cosmic evolution. But empowering because we, despite our smallness, can understand these vast scales. We can measure distances to galaxies billions of light years away. We can reconstruct cosmic history from the Big Bang to the present. We can predict the universe's future evolution. We can look at the night sky and know what we're seeing, understand what those points of light represent, appreciate the vast distances and times involved. Every time you look up at a dark night sky, you're seeing history. You're seeing light that left distant stars years, decades, centuries, or millennia ago. You're looking at a tiny fraction of the trillion galaxies that populate the observable universe. You're seeing the Milky Way, our cosmic home, stretching across the sky, each point of light a sun with its own potential planetary system. You're witnessing, if you look at the right time and place, the Andromeda Galaxy, that faint smudge containing 1 trillion stars, whose light took 2.5 million years to reach your eyes. The universe continues its expansion. Galaxies continue receding from each other. Stars continue forming in distant nebulae. Black holes continue merging and sending ripples through space-time. Cosmic structures continue evolving under gravity's relentless pull. All of this happens on timescales and distant scales that dwarf human experience, yet we can observe it, measure it, and understand it. That's the real miracle, not just that the universe exists, but that we can comprehend it. Before we close, I want to leave you with one final thought. The journey we've taken tonight, from Earth to the edge of the observable universe and beyond, represents humanity's greatest intellectual adventure. Every measurement, every discovery, every insight has been hard-won through centuries of observation, experimentation, and theoretical work. The scientists, astronomers, and researchers who've built our cosmic knowledge dedicated their lives to pushing back the boundaries of human ignorance, to replacing mystery with understanding. Their work continues. Right now, telescopes around the world and in space are collecting photons from distant galaxies. Researchers are analyzing data, refining theories, testing hypotheses. The cosmic frontier keeps expanding as new technologies enable new observations and new discoveries. The universe still holds many secrets: the nature of dark matter, the properties of dark energy, the possibility of life elsewhere, the ultimate fate of cosmic expansion, the behavior of matter and space-time under extreme conditions, and countless other mysteries we've only begun to explore. Each of you watching this can participate in this grand endeavor. Not everyone needs to be a professional astronomer or physicist. Simply taking the time to learn about the universe, to appreciate its scale and complexity, to understand your place within it, represents a valuable contribution to humanity's cosmic awareness. Share what you've learned. Look up at the night sky with wonder. Support science education and research. Ask questions. Stay curious. The universe is vast, ancient, beautiful, and strange. It's bigger than we'll ever fully comprehend, older than human civilization, and filled with more galaxies than we can count. It operates according to physical laws we're still discovering, evolves on timescales that make human history seem instantaneous, and extends far beyond what we can observe. Yet it's also our home, the context in which we exist, the arena where our lives unfold. Understanding the universe's true scale doesn't diminish us. If anything, it elevates us. We are the universe observing itself, thinking about itself, trying to understand itself. We're made of star stuff, contemplating stars. We're patterns of matter and energy that have arranged themselves into consciousness and curiosity. That's not insignificant, that's extraordinary. Thank you for joining me on this journey through cosmic scales. If you found this exploration meaningful, please like this video and subscribe to Nebula Nights for more calm, detailed explorations of astronomical wonders. Share this with anyone who might appreciate a deeper understanding of the universe's true scale. And most importantly, the next time you look up at the night sky, remember what you're seeing. Those aren't just points of light. They're distant suns, perhaps with their own planets, perhaps with their own forms of life, looking back at us across the cosmic void. They're pieces of a universe so large, so old, so magnificently complex that we're only beginning to grasp its nature. The universe is big, incomprehensibly, overwhelmingly, beautifully big. And somehow, impossibly, wonderfully, we're here to witness it, to study it, to appreciate it. That makes us pretty special, even in a universe containing septillions of stars. Clear skies, everyone. Until next time, keep looking up.